The nature of my work or the nature of my research is to understand how evolution happens. And in particular, I'm fascinated by the fact that it's not a uniform process. Sometimes evolution can be really, really quick, as if driving along the Autobahn, at warp speed. And in other cases, evolution seems to plod along at a very slow pace, as though it were inert or nearly so over, epochal timescales, million-year timescales. Why is this? What causes this disparity in evolutionary rate? Why is it lightning fast in some cases, and why is evolution relegated to the slow lane in others? Well, I've discovered that organisms themselves play an incredibly prominent role in dictating the rate at which evolution unfolds. Organisms, through their behavior, are endowed with the capacity to dictate the natural selection that they experience. Now, we know that natural selection is incredibly important for evolution. This was the key discovery made by Charles Darwin over 150 years ago. Now, and natural selection is an incredibly potent force for evolution. However, we have largely treated selection as something that happens to organisms being the subject of natural selection. And while there is truth to that, that is certainly not untrue, it's actually more of a two-way street as opposed to a one-way street. Organisms can actually dictate how much and what types of selection they experience through their behavior, simply by being choosy about where to be active, when to be active, and with whom to interact. And so through their behavior, organisms can, on the one hand, expose themselves to natural selection by using new resources or entering new environments, which in turn should prompt or accelerate evolution. Conversely, organisms can use behavior to shield themselves from selection, hiding from environmental extremes, shielding themselves from certain types of predators, and in so doing, limit the natural selection that they experience and slow evolution down. In other words, organisms are both the subjects and the agents of natural selection. They are not exclusively at selection's whim and mercy, they have agency in the process. I'm an organismal biologist, which means that I study how organisms function, work, live, and evolve in their natural environments. So at heart, I'm a field biologist. And so the field, that is the natural places where organisms are found, is a major source of scientific inspiration and a permanent fount of ideas. I get a lot of the ideas for my work simply by going into the field. I work primarily in the tropics, and bringing my materials with me so that I can spend long periods of time in the company of the animals. And simply by observing them and combining my observations with my reading of the literature and conversation with other experts, I can start to build ideas about what I think might be happening, how these organisms ended up where they are, why do they look the way they are, why are there so many organisms in one place and fewer in others. I can start to stitch together patterns, and based on my connection among those patterns, build hypotheses about how those patterns arose. So the field itself, the organisms, really, the organisms are the OG, the original source of inspiration for everything that I do. It's a very exciting part of what I do, being a professor. Both, I run a lab. I have PhD students, postdocs, lab managers, undergraduates. I have a lot of folks who work in my lab, and we work together to develop ideas, test those ideas, publish them, present them to the broader world. And, working as the lead mentor for the lab is a challenge, of course. It's a daily challenge that challenges me to grow, but it's also really exciting and extremely rewarding, to see your mentees grow in confidence and in capacity. There's such a sense of reward that comes with that, such satisfaction and fulfillment, both as a scientist and as an educator. And I also get the pleasure of, connecting ideas and teaching undergraduates in the classroom and working in the museum to develop exhibits and educational content. All of these hats that I get to wear, in addition to, the muddy boots field biologists and the evolutionary biologist in the office on the computer, all of these different hats present different challenges, but also different sources of reward. And the fun part is that no 2 days are ever exactly the same as a result. It has been wonderful and surreal, I must say. Um, in terms of the research itself, I think it's been the best, most immediate and thorough gratification and reminder that I'm onto something worth pursuing. You know, one of the things about being an academic is that your feedback is pretty infrequent, and often harsh. We take critical feedback on our writing, on our presentations. That's part of the beauty of science, is that we have to always be open to constructive feedback and, go through both joys, which are, relatively infrequent, and also some rejections. That's part of the process. And so at any point in that process, it's very difficult to, see the forest for the trees, or it can be challenging, and get that 30,000-foot view. Like, is this really worth pursuing? Am I onto something here? I think I am, but, what does the broader community think? This award, which is an amazing recognition to receive, comes because a group of folks felt passionately about my work and felt that it really was a valuable contribution to the field, and that I'm onto something worth pursuing. And so I must say, it is the biggest, most energizing motivator to continue doing what I'm doing. One of the things I've developed over the past 15 years is really making this connection between behavior, environment, and evolution, how organisms interact with their environments and how those interactions dictate the rate of evolution. This work has been, fundamentally retrospective. We use the contemporary behavior of organisms to make inferences about phenomena that unfolded over millions of years, right? So we're looking back in time using the present day as a lens. What we're doing now is seeing if we can actually go the other way, if we can be prospective and not just retrospective. What we're discovering is that some organisms, that although behavior is this powerful weapon that organisms can marshal to contend with their environments, it's not a universal conclusion, a foregone conclusion, or a universal outcome. Not all organisms are equally capable of marshaling behavior to their advantage. We're finding that some organisms are able to use thermoregulation. This is the capacity to dictate their body temperature through environmental changes, moving into the shade, out of the shade. Some lizards, these being the organisms we most commonly study in the lab, are able to use thermoregulation better than others, particularly those that live in open or edge habitats where there's abundant sun and shade. Those types of lizards turn out to be incredibly precise thermoregulators. And through this thermoregulation, they're shielding themselves from thermal variation, usually environmental extremes like extremely hot temperatures, and their physiology is very slow evolving, relatively inert. By contrast, lizards in closed canopy forests like cloud forests, those environments are pretty homogeneous. It's pretty shady throughout, right? That doesn't give lizards a lot of behavioral opportunity to thermoregulate, and instead they thermoconform. They don't use behavior to contend with the thermal environment. So we have lizards kind of in these two flavors that have very obvious consequences for physiological evolution. What we've discovered is that it also predicts how they're responding to climate change. What we've discovered is that those open habitat lizards are thermoregulating, and they continue to do so today. And their physiology continues to remain unchanged in places where we've assessed it over the past decade and a half. By contrast, their relatives in the cloud forests, they can't use behavior, right? They're thermoconformers. Their environments do not allow thermoregulatory behavior. Because they don't have behavior in their arsenal, we have discovered that over the past decade and a half, they've become more heat tolerant. They are exposed to selection, and so they are adapting. And so these are initial observations. What we'd like to do is transport those initial observations from the liminal space between early discoveries to a more robust theory. And in order to do that, to see if this connection between habitat structure, behavior, and physiological adaptation is more widespread, is this something, for example, that characterizes lizards more generally, vertebrates more generally, invertebrates? Can we use this framework to more broadly anticipate how organisms are going to be contending with rising temperatures? Because it gives us information that we can use. If we know that they can use behavior, that's going to tell us how they're going to deal with environmental extremes. And so we can manage around that. We can provide them with access to sun and shade, the primary mechanism of response, right? Conversely, if we know they don't have that weapon in their arsenal, we can now anticipate how they might respond instead. So this information is power, and it's more powerful if we can apply it to more types of organisms. So over the next couple of years, we're going to be testing this framework across all types of ectotherm lineages, ectotherms being organisms that can't metabolically regulate their temperature in the manner that we can, as can other mammals and birds. So most animals are ectotherms, and so we're hoping to see if we can create a broader predictive framework to anticipate how ectotherms will be responding to climate change. I must say that as I was growing up, I had no idea that I would become an evolutionary biologist, a professor, a curator, a scientist, primarily because I didn't know that these were jobs that one could do. I didn't know that this was a career that I could access. What I did know as a kid growing up, and I grew up in New York City in Queens, was that I was obsessed with nature. And if you're from New York City, being obsessed with nature presents a fundamental challenge because access to green spaces is very limited. So thankfully, I had the American Museum of Natural History, the Bronx Zoo, the Queens and Bronx Botanical Gardens, Central Park, Corona Park. These were places, any green space, any museum, any zoo, these were places where my imagination and my fascination and wonderment with the natural world could run wild, could run free. These were sources of inspiration to me, and maybe it's not surprising that I've ended up back at a museum, so to speak, because I understand the transformative power that museums can provide by connecting people, with the natural world and finding a place and creating a place where their wonderment can be stimulated and their inspiration can be stoked. So the fires of inspiration can be stoked. I also grew up, I'm first gen American to Cuban parents, and I grew up nursed on their stories of the tropics. And I think as far back as I could remember, I also had tropical dreams. I wanted to go to these places where biodiversity exploded, where there were all types of organisms. I wanted to see the Caribbean, I wanted to see the Amazon, I wanted to see the Indo-Pacific. I wanted to go where the organisms were, and I wanted to see where biodiversity was at its highest. So at the time, I could continue. I thought I would become a wildlife veterinarian. It was the only career that I knew of that would allow me to connect with organisms. I knew about documentaries, and sometimes those documentaries had veterinarians with them. And so I thought this would be my way to explore the natural world. And of course, growing up first gen American, what are the careers our parents tell us we're allowed? There's doctor, lawyer, and engineer, right? So I was working within that scheme. Um, but then I got to college, and I did my undergrad at Boston University. And in my first day of undergrad, I took introductory biology, and the lecture was about the Cambrian explosion, this incredibly important moment in history when many of the animal groups we recognize today suddenly, almost explosively appear in the fossil record. That's why this period is called the Cambrian explosion. It's this explosion of animal life during the Cambrian period. This explosion was about 541 million years ago. And I found it emotionally overwhelming to suddenly have my place in the universe, my place in the world, be drawn back by hundreds of millions of years. And for my story, my story, our story, the story of humans, the story of all living things, to be that much deeper and richer, and to be connected in a cosmic sense to these alien-esque forms that look nothing like the organisms we see today was enlightening, inspiring, and humbling. So it was those pieces together. It suddenly dawned, and at the time, for work studies, I needed the cash. I was working in a lab, and I worked in a neurophysiology lab with a PI, and on day one started helping out with experiments and doing scientific research, and found my thing. You know, the excitement, the thrill of discovery, all of these things in the first few weeks of undergrad happened at once. I knew that I wanted to be a scientist, that I wanted to be a professor, run a lab. And I knew that I wanted to study evolution because evolution is the story of us, the story of living things. It is the reason why life exists in the way that it does. So to really understand biology, to understand organisms and biodiversity, it seemed that the only way I could meaningfully do so was by becoming an evolutionary biologist. It's hard to envision yourself in a space if you don't see anybody like you in that space. And that can mean many, I mean, we know that intersectionality is real, right? So there are many ways that we could either, that we can feel excluded from a space, right? There are many ways by which that could happen. Imposter syndrome, I think we all probably in some shape or fashion contend with that. I will say that I separate self-doubt from imposter syndrome. And I think one of the reasons imposter syndrome is so hard to overcome is because self-doubt, which can actually be adaptive and important, but it can also unfortunately lead to imposter syndrome. So for me, it's about maintaining the self-doubt, and I'll explain why that's important shortly, without venturing into the damaging space of imposter syndrome. So I'm a scientist, right? If we were 100% confident all the time about everything, we would have no work and we would probably be wrong about a lot of things. One of the reasons science works is because we insert through the scientific method and an emphasis on replication, a lot of self-doubt into the process, right? We are constantly testing, retesting, refining, revisiting ideas. And the impetus to do that comes from a healthy measure of scientific self-doubt. Do I have the full perspective? Is what I found in this organism restricted to that organism or more widespread? We can use that self-doubt in an adaptive context to fuel our work and to keep ourselves humble and to keep ourselves aware of the strengths and limitations of the data we've brought to bear on an idea, right? That is important. However, when we start to doubt the work because of our identity and other aspects that feed into who we are as individuals, then that becomes maladaptive, right? And that's not just coming from the individual. There are a lot of societally driven reasons for why people may not feel welcome or directly excluded from a space. And so the work becomes in maintaining the healthy measure of self-doubt without allowing the imposter syndrome to kick in, right? That's the difference between, have I done my best job on this work because I could do more science or better science, versus have I done my best job on this project because I myself don't belong in this space? I would be delighted for folks to reach out. I'm available by email. We have a lab website, www.marthamuñoz.com. We also have a Blue Sky account, so you can find us there as well.